Hi everyone. We're going to talk about vector fields and differential equations, or ordinary differential equations. This ODEs is a whole separate, you could spend your whole life studying ODEs. So we're only going to see a little bit of it, but it's important to see it because it's how calculus comes up in science. Well, one of the ways. So vector fields and ODEs turn out to be the same. They are the same. Now, we've seen vector fields in terms of, if I had let's say I'm in machine learning and I create a loss function. And it's a function that eats my huge image file that has, 1,024 real numbers, each of them corresponding to like a grayscale pixel in an image, maybe. And this loss function will spit out a real number, anyway, we'll learn this later. Then what we would take is we'd take the gradient. And the gradient would be a vector field on 1,024 dimensional space, for example. And we know how to take the gradient. You just take all the partial derivatives with respect to all these input variables, and you put them in a vector. And then you can take a point in 1,024 dimensional space and get out a vector that we call grad f evaluated at that point. And this would be an actual vector, like it might start 5, 2.3, 7, 6.2, minus 1.1, for 1,024 numbers. Okay. And so then that vector field is what we'll sort of follow around. So if we're here in 1,024 dimensional space, we will step this way. Then now we'll be here. There's a new vector there, and we'll step. There's a new vector at this point, and we'll step. And in doing this, we will be training our neural network. But this is just one way vector fields come up. Some vector fields are gradients of functions. But there are other vector fields as well. So what are they? Oh, let me get rid of this. So in science, for example, in chemistry, if you tell a chemist the concentrations of 7 chemicals, say U1 through U7, are the concentrations of those chemicals right now, then the chemist will be able to tell you, based on how much of each of them, they'll be able to tell you essentially how the first one's going to change with time, how the second one is going to change with time, essentially the velocities of these chemicals. They'll be able to tell you that the enzyme will change according to this function. The substrate will change according to this function. In other words, chemistry provides a map from the 7-dimensional space of possible concentrations of 7 chemicals back to that space. And this would be sort of the vector in our vector field. It tells us what's going to happen next to linear approximation. Okay? And so this vector field here, it's not the gradient of some function. No. It's just a vector field that comes from our knowledge of science. So science can produce vector fields. And these are also called ordinary differential equations. Okay? Now, this is not a chemistry class nor a physics class, but now you have a chemistry example. Let's look at a physics example. And this one will actually try to understand a little bit more in detail because it's only a 2-dimensional space. Up here, this was a 7-dimensional space, harder to visualize. But here, consider a pendulum. It's swinging back and forth and back and forth. To describe the state of that pendulum, you just need to know one number, theta, and surprisingly, you also need to know theta dot. You need to know how fast is the pendulum moving. For example, right here you see that little vector. That means that the pendulum is actually moving in this freeze frame picture. We could imagine that it wasn't moving, that we were holding it right there. So this is maybe my hand holding it still. And then the velocity would be 0, and the position would be, I don't know, what is this angle? Maybe negative 1? I don't know. Some angle. And I don't know why I said negative. Maybe we'll take positive angle to be that way, and negative angle to be this way. And so you see that actually I could be holding it still, like here, and then the velocity would be 0 at that moment. And then I want to know what would happen if I let go. Okay? And that is where we're going to move along a vector field in some sort of abstract space, a two-dimensional space, whose first dimension is the theta, and whose second dimension is the velocity, theta dot. Okay? And so we don't have to call it that. We could call it y, and we could call theta x. And now we're just in a space, R2, with x, comma, y coordinates. And now what I'm going to do is tell you a vector field. Now this comes from physics. It sends x, y to the point y minus x. So this seems like a silly thing. You just flip the two and then put a minus sign on one of them. But this actually determines, this vector field determines the behavior of a pendulum that's swinging around. And that comes from physics. How did we know to write down this vector field? Well, it's from our knowledge of physics. So it's sort of weird because in physics, often you need to know positions and velocities. And then you're set. And this is because of Newton's law about acceleration is actually determined by forces. So we don't need to figure out what acceleration is. We will know what acceleration is based on this equation and our knowledge of the physics of what's going on. For example, the pendulum has gravity pulling it down. So if I let it go right here, gravity would be pulling down, and that would make it swing in this direction. Okay? Now, this is the basic idea, is that you need to know positions and velocities, but then accelerations are already determined. Now, what that means is that once we have this vector field, and if we know that we're starting at this point right here, then the vector field will tell us move down. Why? How do I know that? Because this is the point, well, I don't know what point this is. Pi over 2. I don't know what this point is, but let's say it's 1, 0. Then the vector field is going to be, well, flip them, and then put a minus sign on the second one. 0, minus 1. And that is this vector. It's pointing downwards. And so that's how we know that at the next moment, the position will roughly stay the same, and the velocity will start to increase. It'll start to, or I guess decrease, because go down. But anyway, it's not, at first here the velocity is 0, but now it's going to start being non-zero velocity, because we're moving down. Yeah, so then we'd be here, and now we've got, we've got some velocity, and then we'd step, and then we'd step, and we would start to predict what the pendulum will do in the future based on this vector field. Okay. Summary. Yes, vector fields come as gradients of functions, like in machine learning. But vector fields also come from science. They come from understanding physics. And wherever they come from, if we know where we are, then we can predict the future by using the vector field and making tiny little steps. This is called Euler's method, which you can see movie Hidden Figures. And we watched a little bit of that in class.